This is Tiago from Coderversity, and in today's video we are going to learn how to master collections in C#. Today you will learn all about lists, dictionaries, hash sets, queue and stack, arrays versus collections, and some best practices tips and common pitfalls. And for that we will use C# and .NET technologies. So what are we waiting for? Let's dive in. Collections are a fundamental part of every developer's toolkit. They allow us to storing, managing, and manipulating groups of data efficiently. What are collections? Collections are data structure that allows storing and managing multiple values in a single object. They support adding, removing, and accessing data in a structured manner. When dealing with a large amount of data, collections provide mechanisms to group similar or related data types together, which makes accessing and processing them much easier and more efficient. Let's do an overview of some common collection types. There is a list, that is a dynamic array that grows automatically to accommodate new elements. A dictionary, a collection that stores data in key value pairs, allowing for fast lookups based on a unique key. A hash set, that is an unordered collection that ensures uniqueness. Every element is distinct. A queue, a first in, first out FIFO collection, like a real-world line where the first one is the first one served. And last, the stack, a last in, first out LIFO collection, where the last element added is the first one removed. These details and about the collections will be covered in detail with real-world use cases, code examples, and some performance considerations. So let's start with the list, the dynamic array. The list, this is how you declare a list, being the type T, a generic type, for example, a list of int called numbers, and then we initialize like this. And let's create here a list with 1, 2, and 3 elements. A list internally uses an array to store its elements. The size of this array is its capacity. As elements are added and the internal array reaches its capacity, it automatically resizes by creating a new, larger array and copying the existing elements to it. This is why you often see exponential growth, so doubling in size, in the capacity of lists as they grow. While adding an element might occasionally be expensive due to resizing, on average, list operations like adding elements have an O of 1 time complexity. This is because resizing happens frequently as the list grows. So let's get an example and add a number 4 to the list. And then to remove, we just type numbers.remove the element 2. Then, in order to access the first element, we do like this. Because all the arrays start in the position 0. Some performance consideration that you should have is that accessing elements by index is a complexity of O of 1, since lists are backed by arrays. However, operations like inserting or deleting elements in the middle of lists have an O of n time complexity, because all elements after the insertion point need to be shifted. By default, the capacity grows dynamically as needed. However, when you know the approximate number of items you'll need, you can optimize performance by setting the initial capacity to avoid unnecessary resizing options. So, what we can do is pre-allocate capacity for a large list, for example. So we can do like this, and then we say array of int, and then we set the constructor with a capacity of 1000. Lists are useful when you need random access to elements or when the size of the collection changes dynamically. They are ideal for cases where you need fast lookups by index or need to add or remove elements from the end frequently. An example is, suppose you're building a shopping cart feature in an e-commerce app where items can be added or removed dynamically. We can do something like list of string that will simulate the cart items, and then we just add some items, for example, a laptop or a mouse, and then we can even remove the mouse. As a best practice, you use list of t, being the t any type that a list can store, when you need flexible storage of data that requires an efficient random access by index. Be mindful of performance when frequently adding removing items from the middle. Next up, we have the dictionary. A dictionary is a collection of key-value pairs and can be initialized like this. Dictionary of a string being the string, the key, and an int being the value that will represent student grades. This makes it ideal, like I said, for fast lookups based on keys, rather than using index position like in a list. How do dictionaries work? Internally, dictionaries are implemented as hash tables. Each key is hashed into an integer, which is used as an index to determine where to store the corresponding value. An hash function. A good hash function is crucial to ensure that keys are distributed uniformly across the hash table. If two keys result in the same hash, a collision, the dictionary handles this using various techniques, for example, chaining or open addressing. Dictionary operations, like adding, removing, and access elements, generally have O of one time complexity because they rely on direct indexing into the hash table. This makes dictionaries much faster than lists for operations like searching for elements by key. So, for example, let's say that we want to add the key Alice, that represents the key as a student, and the grade of 90. And then we can also add another way via indexer, so like an array. And Bob will have the grade of 85. This is the same thing with two different syntaxes. And now, for a fast lookup by key, we can do like, if we want to get the Alice grade, we can do something like student grades, and then in order to search, we search always by key. And this is a fast lookup by key. O of 1 for most operations like adding, removing, or accessing by key, this has. However, in cases of hash collisions, performance may degrade to O of n for worst case scenarios. Dictionaries can be more memory intensive than other collections due to the need of storing both keys and values, as well as the overhead of the hash table. For example, imagine you're building a library system where you need to store books with unique ISBN, that is the unique numbers to identify books, and we declare a dictionary that will have a key string and values string as well. Let's call it library. New dictionary string, just initializing. Then we will add, for example, let's say 978, and then some numbers, random numbers, being the ISBN, and then we just put the value that will represent the title of the book. Let's do the same thing, but with a different key, of course. And let's call it the Iliad. So as a best practice, you always use, not always, but as a best practice, you can use a dictionary with key value when fast lookups by key are required. Be sure to check if the key exists using contains key method, for example, library.contains key, before trying to access it to avoid runtime exceptions. So for example, to simulate a check, we can do something like if students grades sorry, I was stuck in the previous example. If library.contains key, and for example this key, or any key that you want, we can do whatever we want here. Now let's dive into the Hashset to ensure uniqueness and fast lookups. A Hashset is an unordered collection that ensures uniqueness. It is ideal when you need to store a set of items and ensure no duplicates. Like a dictionary, a hash set is based on a hash table, but it only stores values, not key value pairs. The hash of each item is used to ensure that no duplicate values are added. This is how you declare an hash set. And the type of the values, let's call it unique numbers. And let's initialize it to 1, 2, and 3. When adding an element, the hash set checks if the element already exists by calculating its hash and comparing it with the existing hashes. If a match is found, the new element is not added. Hashset supports common set operations like union, intersection, and difference, which are efficient due to the hash-based nature of the set. So, what would happen, having this said, if we do this? Remember to check the values that already exist, and this is a hash set. Of course, this won't add because the 3 already exists. However, if we do like this, it will add successfully the 4 to the set. The performance of the hash set is O of 1 for add, remove, and lookup operations. Since Hashset is backed by a hash table, it provides a constant time operations for most actions, even for large data sets. An example scenario, you can suppose that you're building a system to track unique user IDs. So let's call it user IDs, and let's put the type of this as string and not initialize it with values. Instead, we will do user IDs dot add, and let's add a unique value of user 1, and then we can do the same for user 2. And then what happens if we try to the user 1 to add the user 1? The duplicate will not be added, of course. As a best practice, you can use hash sets when ensuring uniqueness is a priority. It is ideal for scenarios where duplicate values would cause issues, such as managing unique identifiers or tags. Next up, we have the queue and stack, some first in, first out, and last in, first out operations, respectively. A queue follows the, like I said, first in, first out principle, where the first element added is the first one to be removed, much like a real-world queue. The queue is implemented as a circular buffer, meaning it keeps track of the front and rear position of the queue. As elements are added in queued, they go to the front to the end, the rear. When elements are removed, dequeued, they are taken from the front. So, for example, let's add a queue of string. And then let's enqueue a customer 1 and also a customer 2. Ideal for handling world scenarios like customer service queues, where the first person in line is the first one served. So, the next customer will be the result of a dequeue of this queue, because this will remove this customer 1 and retrieves the next one in file. Not in file, in queue, sorry. And the next customer will be then the customer 2. Now, for the stack, a stack follows the opposite, the last in first out principle, where the last element is added and the first one to be removed, like a stack of books, for example. The stack works by pushing elements onto the top of the stack. When you need to remove an element, you pop it from the top. So let's change this to stack. Let's keep the strings and let's call it stack. And then the stack inserts values by calling push. Let's add in page 1 and page 2. And then, if we want the last page, how do? We do last page stack dot pop. And this will remove what? Remember that this is a last in first out. So the last was the page 2, so it is the first out, and the last page will be the page 1, because it removes the page 2 by calling pop. This is ideal for scenarios like undo or redo functionality or navigation history in applications where the last action performed is the first one to be undone. Now let's talk a bit about arrays versus collections. Arrays are fixed size collections, while collections like lists are dynamic in size. Each list has its advantages depending on the use case. The arrays are faster because they have direct access to the memory. However, since arrays are of fixed size, they can't grow or shrink dynamically. For example, if we want to declare an array of integers with numbers, we have to give it a fixed size, for example, of 5. While, in contrast, the list grows dynamically, providing more flexibility at the cost of potential resizing overhead. For example, the numbers list as new list of int, it has a dynamic size. Use arrays when you know the size of the collection in advance and want faster access. Use collections like the lists of wherever you want when you need dynamic growth. Some best practices and common pitfalls. For performance optimization, if you're using a list and you know the approximate size, pre-allocate capacity to avoid resizing, even if it's dynamic. So for example, a list, large list, equals to new list of int and 1000 to pre-allocate space. How to choose the right collection? Choose lists for ordered collections with dynamic sizing. Choose dictionaries of a key values when fast lookups by key are critical. Choose hash sets when you need to enforce uniqueness, and choose queue or stack for first in, first out or last in, first out behavior. To avoid common pitfalls, for example, for the dictionary, always check for the key existence to avoid the exceptions, like we did with the example of the student grades for Alice. As a bonus tip, I will talk a bit about advanced collection types. For example, we saw the list and now we will check the linked list. A linked list offers fast insertions and deletions at both ends of the list. For example, this is how you declare a linked list, pretty much similar to a list. Let's call it linked list equals to new linked list. And now we have access to the end of the linked list and to the start. So if we want to add last, we do like this. And if we want to add first, we do like this. So this adds to the end, and this adds to the start. Also, we have observable collections. This is used primarily in UI applications, for example WPF, for data binding. It notifies listeners when changes occur. It's behavior very similar to the observer pattern. If you are interested in design patterns like this one, the observable, check out the video in the description that I talk about my top 5 design patterns. Now, example. Observable collection of, let's say, string items equals to new observable collection of string, and we initialized. And then let's say we change the collection and we add like this, that is a lambda function, and what the notification will be, for example, just to simulate, the notification will be collection changed. So this is the same as putting something like this, items dot collection changed plus this, but with sugar syntax. So plus equals, it's the same as having collection changed equals to collection changed plus these two parameters. And then we notify with a console write line. This is just an example. You can have whatever you want here as the lambda expression. So, as a recap, please check again each collection type and their use cases, and focus on how each one serves a particular role in C# programming. The importance of choosing the right collection is based on the requirements of the applications, for example, the performance, the data structure, and the use case. I encourage you to explore further by using these collections that I just presented in your own projects and continue learning about advanced topics, like, for example, concurrent collections. For example, a concurrent dictionary or other custom collections. And that wraps up our tutorial. I hope you found these projects helpful and that you learned something new along the way. If you followed along, congratulations on completing the project. Don't forget to like this video if you enjoyed it, and consider subscribing to the channel for more programming tutorials and projects. If you have any questions, suggestions, or just want to share your own version of the project, drop a comment below. I'd love to hear from you. Thanks for watching and happy coding. See you in the next video.